Imagine a village separated from the neighboring town by a creek. For generations, people crossed by walking through the water. And during the rainy season, the creek became dangerous and travel stopped. So one day, a villager built a wooden bridge, not because anyone asked, but because she needed it for herself. Soon, everyone used it. Months later, someone added a better plans where the surface was had become slippery. Another installed railings after witnessing a fall, and someone else added lamppost for safer travel at night. No one was responsible for that whole bridge, and yet everyone contributes. Every contribution made it better for everyone. That is how open source works. Contributors improve software because they experience a problem and know how to fix it and choose to leave the project better than they found it. Now, place every person in this story inside the same organization. The bridge become an internal software platform. The villagers become engineers from different teams. The motivation remains unchanged. Contributors improve software because they depend on it, not because they were assigned to it. And that is inner source. The bridge is same, only community changes. Now, AI tool can now help every contributor build faster and with great confidence. The question is no longer whether to use AI in InnerSource. The question is how to use it correctly, effectively, and efficiently. Dear wonderful people of InnerSource community, my name is Amburi Roy and I am from eBay. Today, I am presenting leveraging AI in InnerSource. In InnerSource, every contribution follows the same journey: discovery, comprehension, execution. Discovery is identifying the right repository among hundreds of internal projects. Comprehension is understanding that repositories, architecture, coding convention, and domain-specific knowledge. Execution is producing a contribution that meets the quality standard of the team the contributors have never worked with. The promise of InnerSource is significant, and so are challenges. Over the year, InnerSource community has developed proven patterns to improve the contribution experience. You can get to know more about InnerSource patterns in here. Patterns innersourcecoms.org and the GitHub InnerSource patterns in this repository. These patterns have been adopted successfully across many organizations, and they have solved the right problem, but they operate at human speed. AI changes this equation. At each stage, there is friction, and at each stage, AI can remove it. InnerSource scales collaboration, AI scales productivity, and together they have potential to scale software development itself. Contributors often know what they want to build, but not where that works belong. Searching manually through hundreds of internal repositories is slow and imprecise. The InnerSource portal makes project visible across the organization. Traditionally, contributors search these keywords using keywords. With AI, they can now ask, let's say, which service owns payment retry logic, or who are the trusted committers for the shipping domain. The portal surfaces repositories, owners, and contribution guideline in one place. A practical AI solution is retrieval augmented generation pipeline, RAG pipeline. Each part solves a different retrieval problem. Vector store, knowledge graph, LLM query layer. So vector store is, let's say, the keyword search fails for intent. A repository name checkout resilience won't surface for the payment retry logic. Repositories are indexed into vector store like Pinecone or OpenSearch using embedding for OpenAI. So contributors find the right repository even when they don't know what it called. The vector find the relevant repositories but do not understand relationship. A knowledge graph built in Neo4j or similar store captured the repository dependencies, service interaction, API contracts, team ownership, and code owner file, building the repository specific context that makes discovery structurally aware, not just semantically close. The contributors ask in natural language. Tool like Glean or Source Graph, Cody bridge both of these two systems simultaneously, querying the vector store for semantic match and graph for the structural relationship. Then they synthesizing a ranked answer with supporting evidence. Now, discovery become a conversational rather than a search. After finding the right repository, contributor face a different challenge, understanding it. How is it organized? What convention does it follow? Which architectural decisions constrain the future changes? That is comprehension. And let's start with documentation. Three inner source patterns govern it. Standard-based documentation ensure every repository carries the same foundation: README, contributing guide, code of conduct. The common requirement defines what every repository must document regardless of team or domain. And document your guiding principle makes the team's value and the decision-making criteria explicit. So contributor understand not just what the code does, but why it was built that way. And together, this gives every contributor a common floor to stand on. But documentation is only good as its currency. Skills agent, sub-agent running as an agentic workflow can keep this file current automatically. detecting when a README, contributing guide, or code of conduct has drifted from the code base and surfacing updates for the steward, core team, or trusted committer to review. AI tools like Copilot, Cursor, or Claude read these files as a repository specific context and answer design question in natural language. What previously required assembling knowledge from readmes, areas, wiki page, Slack thread become available through one single chat interface. Hours of exploration compressed into minutes. The Model Context Protocol, or MCP, enables that experience by connecting AI tools to all of those sources. The contributor asked a question, the tool reached out across every connected sources to answer it. Taken further, the LLM does not just read documentation. It can derive the context specific, repository specific context directly from the code base on every run. It reads the source code, infer the naming convention in use, identifies the pattern that appears repeatedly, and reconstruct the architecture from the structure it observed. The context is always as current as the last commit. But deriving context from the code every time introduce three failure mode: token inefficiency, bias, and non-determinism. Token inefficiency because the tool reads every file to extract a fraction of useful signal. Biases are inevitable when deprecated pattern dominates legacy code, leading the LLM to incorrect infer these pattern, which reflects the team's or repository's current standard and best practices. Non-determinism because different run can interpret the selective code base differently. There is no authoritative version, and the contributor has no way to know what tool decide to believe. This is a deeper challenge. Connecting sources solve access. Deriving from the code base solves freshness, but neither gives you the accuracy or authority. The question is how to make this repository-specific context explicit, curated, and trustworthy, so that what the tool read is what the team actually intend. We will come back to this. Discovery answered, where does this work belong? Comprehension answered, how does this code works? Now execution answered the hardest question of all. Can I build something this team will accept and stand behind after it ships? Execution unfold two phases: generating an implementation plan and carrying it out. The first phase is generating a plan. Before a single line of code is written, the contributor need to know what are they building, which components are involved, and what constraints applies. AI provide that requirement analysis grounded in repository-specific context by identifying which components are involved, which boundaries must be respected, which patterns apply, what is the recommended approach, and what are the trade-offs are, and which alternatives are considered. The inner source pattern for this step is transparent cross-team decision making. The contributor publishes the implementation plan for reviewing with the trusted committer and code team before writing a single line of code. They recommend changes aligned on direction, and only then the implementation begins. This front loads judgment to where it costs least to apply. Once the plan is reviewed and approved, the contributor builds. And these unfold across 4 stages: code generation, code review, deployment, and post-production. Code generation is where most of the AI tools play today. Copilot, Cursor, or Claude generate code, test, documentation, pull request. When grounded in the repository-specific context, they generate the contribution aligned with the team's engineering standard, correct naming convention, respected architectural boundaries, approved error handling pattern, and test consistent with the project's testing strategy. Without that context, 3 failure mode emerge: lost in generalization, truth drift, and AI fatigue trap. Lost in generalization is, let's say, the tool defaults to the pattern from the training data or general understanding, producing the code that is technically valid but architecturally wrong for this repository. For example, a contributor add a new payment provider using conventional implementation. It complies, it passed test, but during review, the trusted committer explained that every provider must go through the payment provider registry or the payment orchestrator, because the direct invocation bypass the fraud checks and the audit log. Now contributors rewrites the tool, but here the tool generalized and the architecture disagree. And that is the lost in generalization problem. Now, code moves, but documentation doesn't always follows. A contributor implement retry logic through the retry policy interface, because that is what the documentation says. The trusted committer flag it. The team migrated to a resilience model 8 months ago, and retry policy is deprecated. The documentation never caught up. The tool was confident. The context was stalled. The output was wrong in a way that looked completely intentional. And that is the problem truth drift. When a contributor uses generative tool without repository specific context, the tool generate generic code that fails review. The contributor corrects and resubmit. 2 or 3 or more than that cycles later, contribution land. After enough repetition, contributor distrust the tool and put more and more human gates, discarding the benefit of automation. The tool intent to accelerate them has become an additional process burden. AI tool fatigue is symptom. Missing context is the cause. All three failure modes share same root cause. Generative tool cannot distinguish what is current or the local truth and the repository specific from what is generic or outdated. So all three are retrieval failure. Repository specific context maintained, versioned, and automatically check for drift address all three problems. With code written, it goes to code review. The trusted committer and the core team remains the quality gate. Every pull request pass through the human review before merge, following the human in the loop principle. Before the trusted committee sees a pull request, an AI pre-screen it against the documented convention using Code Rabbit or custom PR review bot, or let's say skill-based agent built on any LLM API with repository specific context as a benchmark. Now, human review then focus on design decision, engineering judgment, rather than correcting same documented conventions. So the contributors' velocity convert into actual throughput. Now, once the pull request is approved, the code ships. The CI/CD pipeline with Circle CI or Harness or Datadog Bits AI automate the verification and deployment. AI integrated into the pipeline to detect anomalies, surface the configuration issues, which is very common, and accelerate the path from the approved PR pull request to production. Now, shipping code is not the finish line. Production is where the real game begins. The InnerSource patterns for this is 30 days warranty. It holds contributor accountable for the stability of their code after deployment. AI supports post-production stability. AI bug triage is when a bug is surfaced, AI answered, which team's code is this? How severe is it? What is the recommended approach? And what are the alternatives? Now, indexed repositories and knowledge graph assign that bug to the correct team and surface the resolution options, all grounded to repository specific context. Resolution follows, then is AI bug resolution. And resolution follows the same path as code generation. And same failure modes also apply. Stalled context here mean the wrong fix and delivered with same confidence. Now, third and the most important here is the emerging pattern analysis. Individual bugs are visible, but pattern across the bugs are not. A knowledge assistant running RAG over recent incidents, combining with the predictive defect analysis powered by observability AI and incident correlation, surface the reoccurring failure pattern of before they become systematic. Now, let's take a pause for a moment and look back the ecosystem. We started with discovery, moved through comprehension, and followed by execution. These are not the collection of AI features. Together, they form an AI-enabled inner source ecosystem where every stage of contribution lifecycle is connected to the next. But there is something even more interesting. Every parts of this ecosystem depend on the same foundation, repository specific context. Discovery depends on it, comprehension depends on it, code generation, code review, bug triaging, bug resolution, all rely on it to produce accurate, trustworthy result. Even failure modes we discussed, lost in generalization, truth drifting, and AI tool fatigue can be traced back to missing and stall and incorrect repository specific context. Everything we discussed depend on this one foundation. And let's dive in. So far, we discussed why. Now, what is repository specific context? Every repository has rules that everyone on the team knows that a repository specific context. The architecture, the coding convention, the test strategy, the design constraint, the team agreement, these are not generic software concept. These belongs to this team. These belong to this code base, and these are the set of decisions. In short, the repository specific context is the current local truth of the repository. The first instinct is where we should keep it. The first instinct is to use what already exists. Most organizations have Confluence pages, wikis, and shared documents describing their system. Can we connect those to the AI tool via MCP and call it done? Yes, of course, we can. But there are trade-offs. Connecting AI tool to external documentation through Model Context Protocol or MCP introduce infrastructure and governance overhead. The unstructured documentation is also token inefficient. The tool reads long pages to extract a fraction of useful signal. The documentation for human is verbose by design, heading, narratives, context for the reader, and the context structure for AI is efficiently concise by design. Signal, no filter. So research shows that the difference is the context efficiency can be up to 70%. The second option is to keep a structured context store separately from the code base and connect it via MCP. This addresses the token efficiency, but infrastructure overhead remains. And now there is a versioning problem. Contexts that evolved independently from the code may refer the pattern that no longer exists, the same truth drift problem. Code generation and code review runs off different versions. The maintenance burden grows. The third option and the AI code generation context pattern recommend is to keep the context near to the code. in the repository itself. When context leave with the code, it evolves with the code. The maintenance burdens drop, the infrastructure burden drops, and because the context file are plain markdown, they work with any AI tool, Claude, Gemini, Copilot, or any custom LLM you are using. Switch tool, migrate model, no change required to the context file. One context collection for all the workflow. Now, how to build it is repository specific context is the knowledge. The context stored is how we capture, maintain, and version the knowledge. The AI code generation pattern recommends implementing it as a structured collection of file in the repository root as the each documenting one aspect of the code base so AI tool can read it, applied it when it needed. The three files forms the code. One, architecture MD maps the code base with component structure, key decisions, and what this repository explicitly does not own, preventing the most common class of architectural error. README tells contributor which context files to attach for the new feature, bug fix, refactoring, or how to load this in their specific tools like Claude, Copilot, or Gemini. Prompt MD provide a structured copy-paste prompt template that have context preloaded so that when contributors start every session with the repository knowledge already attached to it, not as a blank prompt. Now, it might sound that creating this context store might be very complicated, but actually creating it is very simple. Just write a prompt. Point a AI tool at your code base, your areas, your contributing guide, and ask to generate the initial context file. A steward, a maintainer, core team, or the trusted committer fills the gap and it is ready to use. For example, a contributor developing a payment feature attach architecture MD and the context, which is payment domain MD, to the prompt. The tool now knows what is the correct naming convention, placing, and what is the correct place correct place for this class in which module and write error types. So the first pull request passes review only on first attempt, or the discussion may be on the design specific. Let me show you a quick example of the context store. Now, I have forked one of the open source Spring project, which is Spring Pet Clinic. And here is the prompt that I have used it. Very simple prompt. First is the role, and then what is the source of truth, what will do if there is any conflict, and even the standard or not to apply the generic convention. Then what is the structure of this folder? This structure actually came from the AI code generation context, which is available in the InnerSource pattern. You can see the context and forces, but if you go to the solution, here is the context store. These are the core files, and this context folder will have all the other contexts. And this part is optional. Now, if you go here, you can see that there are 3 core files, and the context files are also generated from this simple prompt with role, with authority, what is the rules for this, how to build it, and what to verify at the end. So this is how, this is simple. With this simple prompt, you can start using the AI code generation context pattern and generate the context store. 3 failure modes degrade the context store, can degrade the context store over the time. First, context overloading. Second, context poisoning. And third, context confusion. Context overloading is too much context. A file that tries to cover everything covers nothing well. When context file grows too large, they fail into the middle, the lost in the middle trap. Signal drowns in noise. So keep each file scope to one topic. Context poisoning is when irrelevant, misleading, or stalled information cause the tool to produce incorrect response with full confidence. A context file with the reference, a model path that was deleted last quarter, or describe a pattern that team deprecated, poison the every response that reads it. And context confusion is conflicting context cause the tool misinterpreted the intent and generate inconsistent responses. So two files describing the same pattern in a different way force the tool to guess which one to apply. Now they will not tell you what they are guessing. So that is a big problem. Now, how we would like to mitigate that? That will be topic for another day. Before you leave today, I would like to mention 3 points. First, pick your most active InnerSource repository. Create one file, just architecture.md, 200 to 500 words, and what that repository owns, what it does not, and where the boundaries are. That is enough to make the first difference. Second, write a prompt. Use the demo as the starting point. Point an AI tool at your code base and ask to generate the initial context files. Review what it produces, and you will have the working context store before the end of the week. And third, please share your learnings and experience. This is how InnerSource pattern improves. If AI code generation pattern works in your organization or it breaks in a way that we have not anticipated, bring it back. The feedback is how the pattern gets stronger. You can reach out to me via LinkedIn or the InnerSource Slack channel. The pattern exists. The demo is live. Start with one file and watch it thrive. Wow, that's rhyme. But I can tell you that's not my, poetry is not my expertise. Remember the bridge? The villager who built it did not wait for the perfect specification. She built it what she needed. Others improved it, add planks, someone add railings, someone add lights. No one owns the whole bridge, and yet every contribution makes it better for everyone. The context store works the same way. Someone creates the first architecture.md, a contributor used it, finds gap, and fill it. The trusted committer review a pull request that passes on the first attempt and notice something changed. The review is now conversation about design, not the correction of the same documented convention. The contributor is not exhausted, so they come back. That is the compounding effect InnerSource InnerSource always promised. AI is just force multiplier when the context is right. The bridge is same, only the tools are faster. Thank you so much for your attention.